Hello everyone, welcome back to your physics teacher, and today we're going to be looking at section 1.5 from the Nelson textbook. So here you were just recently introduced to the big five kinematic equations of motion, and we're going to be looking at how we can use them to solve kinematics problems in one dimension. So in the first screen that you see here, I listed them in the order that I put them in importance. So you can see that we have the most important, the first equation, second, third, fourth, and fifth. So it looks a bit different than it is in the textbook. It's just because I find that this is the ones I use most common to the one I rarely use. So the most common is equation 1, 2, and 3. 4 and 5 you're rarely going to use, but if it makes you feel safe, have it there at your disposal. We might need it in this case. I'm not sure. I haven't tried the questions before. So hopefully we can do it together. Now, let's start off by looking at some examples. So we're going to be looking at example number 1. So here we have a car accelerates from rest at a rate of 2 meters per second squared north. What is the displacement of the car at t equals to 15 seconds? So let's try to draw a car. And we're going to have to try to interpret words into numbers. So whenever they say a car accelerates from rest, then that is giving you a hint. If you're starting from rest, how quickly are you moving? Well, you're not. So initially, your velocity then is going to be 0 because you're starting from rest. And then you're going to be accelerating, and at the end of this acceleration period, your final velocity is 2 meters per sec. Oh, wait, no. They give you the acceleration. So the acceleration is 2 meters per second square in the north direction. And they're asking you, what is the displacement? Well, you're starting from rest, and your acceleration is up, so your displacement is in the upwards direction. Your displacement is your unknown in this case. And because all of these quantities are vector quantities, you should be thinking about the direction as well. So that's why I put the displacement going up. And this whole acceleration takes place during a time interval of 15 seconds. Alright, so they're asking us for displacement. We have the initial velocity, the acceleration, and the change in time. So notice that the first equation, which is always my main go-to to check first, we have the time, we have the acceleration, the initial velocity, we have it too because it starts from rest, so that was 0, and we're looking for displacement. So it's really easy, it's as straightforward as using the first formula. So let's use the first formula here. Now, because we are dealing with vector quantities, you have to consider the directions of the vectors carefully. So let's assume the north is going to be our positive direction. So this is going to help us out because when we're putting in the values, our displacement was pointing up, so that's positive delta D. Our initial velocity is 0. Our acceleration is pointing up, so we can write that as a positive value, delta t squared. So now we put in the values of the magnitude from the numbers that we were given. So our displacement is 1 over 2 times 2.0 times 15 square. And here we plugged in the values and didn't have to convert the units because time was in seconds and the acceleration is in meters per second square. So let's just calculate this then. So this gives us that the magnitude of the displacement is 225 meters. And because we were dealing with vector quantities, we have to state that the displacement, which is a vector quantity, is the magnitude, which is 225, and the direction is north. Okay, so that's a good warm-up for you. So let's see if we can do more difficult questions. So number 2, an astronaut is piloting her spacecraft toward the International Space Station. So we have a spacecraft. I love the spacecraft questions. Let's SpaceX, right? Okay, so this astronaut is piloting her spacecraft towards the ISS, International Space Station. So to stop the spacecraft, she fires the retro rockets. So that means if she's trying to go up, the retro rockets will be pushing up, making her go down, which causes the spacecraft to slow down from 20 meters per second. So from is her starting speed. So her initial velocity. Oh, I got too ahead of myself. She's traveling east, so we're gonna have to rotate this. So her initial velocity is from 20 meters per second east. And because velocity is a vector quantity, a good idea is to try to draw the vector as well. So once she turns on the retro rockets, this means that the gas comes out this direction, which pushes her backwards, right? And this is going to cause her spacecraft to slow down from 20 meters per second to 0. So that means to 0, her final velocity is 0, right? Because you're coming to complete stop, I suppose. And this time interval takes 12 seconds. So they're asking us to find what is the acceleration of the spacecraft, and B, what is the displacement of the spacecraft? Okay, do we have any other information? We don't have the acceleration, which is what we're trying to find. So in our formulas, we're going to go look for something that includes time, initial speed, final speed, and looking for acceleration. My first one is the first equation I usually check. So I'm looking for my acceleration, but notice I don't have displacement, so this is not a good choice for now. My second formula, my final velocity I have, initial velocity I have, acceleration I don't, but we know the time interval. But the acceleration is trapped there somehow, so we're going to have to rearrange the equation. So we're going to use equation 2, but we're going to have to rearrange it to find the acceleration. So let's rearrange this equation. So V final minus V initial equals to A delta T. I brought the initial velocity to the left side. And to find acceleration, I just divide both sides by the change in time. V final minus V initial over delta T equals to A. So this formula, we actually used it before, right? That's how we define acceleration, is the change in velocity over the change in time. So you didn't have to use equation 2 in this form. You could have just used it in the original form. It's the same thing. All right, Ben, before we plug in the values, let's use our convention. And let's assume the east is going to be our positive direction. Let me move this for now. So final velocity is 0 minus v initial is 20 meters per second east, but east is positive, so we could just write 20. Change in time is 12 seconds. So our answer is negative 20 over 12 minus 10 over 6, which is minus 5 over 3. Right, I'm just reducing it. And because we got a negative value, once we put back into the acceleration as a vector, this can be written as 5.3 meters per second square west. Which makes sense, right? Because if our object was moving to the right and slowing down, that means the acceleration is going the opposite direction. So our acceleration was going left. So we're likely to be correct. We got a negative value, which means going west. For the second part, now we're looking for displacement. So let's go back to a formula sheet. And again, I always start from the top. We're looking for displacement. We have initial velocity, we have the time, we have acceleration now, and we have the change in time. So we can just use equation 1 now. And because we're dealing with vector quantities, don't forget you have to consider to the right is positive and to the left is negative in this case. So our delta D, we're going to leave it as a vector. Our initial velocity is to the right, so it's a positive quantity. 20 times 12 plus 1 over 2. Acceleration was west. We have to change that to be negative 12 squared. So let's calculate this. My displacement, we get a positive value, 120 meters. And because we got a positive value, this is 120 meters east. Which makes sense because the rocket was moving to the right, so the displacement should be east, which is to the right. And it was about 120 meters. I'm not sure if that seems reasonable because we're talking about space scale. Could be right, but it looks correct. All right, if you're still with me, I appreciate it. Otherwise, please keep in mind that you could select the part of the video that you have trouble with, so you don't have to watch the full thing. Just go to the part that you had trouble with, so that way it's going to be making it easier for you. Let me drink some water too. So for question number 3, we have a helicopter traveling at a velocity of 50 meters per second west, accelerates uniformly at a rate of 7 meters per second square east for 4 seconds. What is the helicopter's final velocity? So here we're going east and west. Let's draw our helicopter. Okay. Oh, the helicopter is traveling west, so I should flip this. Not sure how to flip it. Okay, I'm just gonna redraw it then. Sorry for taking up your time. Sorry about that. Now we have a helicopter traveling at a velocity of 15 meters per second west. And again, we're dealing with vector quantities, so it is a good idea to visualize them by drawing them. So west pointing. And this is the initial velocity, right? Because this is what it was traveling with already. And it's telling us that at the end of 4 seconds, so after time interval of 4 seconds, the velocity of this helicopter is what's missing. So we don't know what the final velocity is. So that's our unknown. What we do know is that during these 4 seconds, it accelerates uniformly at 7 meters per second square east. So it's to the right. So notice that whenever they say the word uniformly accelerating, means that the acceleration value does not change. So it doesn't mean uniform motion where the velocity value doesn't change. So when they say accelerates uniformly, the acceleration does not change. And because our acceleration vector is to the right and our velocity vector is to the left, we suspect that this is going to be slowing down. So we know we're going to be correct if our final velocity is lower than 15. So let's try to see if we can calculate that. But in order to do that, let's go look at the equations. So here we have nothing to do with displacement. So let's go see our equations. So right away, equation 1 is no good. Equation 2, final velocity is what we're looking for. We have initial velocity, we have acceleration, and we have the change in time. So it looks like we're going to be using equation 2. See, that's why I told you, rank them in terms of importance. So first check the first, then the second, and the third. It makes it a lot easier. All right, and because we're dealing with vector quantities, once again, make sure that you set your convention that east is positive. So when we put in the values, the final velocity, we don't know. And if you don't know that direction, just leave it as a vector quantity. So don't put a negative or positive. The initial velocity was to the left, which is negative, so we put negative 15. Our acceleration is to the right, so we leave it as positive 7. And our change in time is 4 seconds. So leave the final velocity as a vector, and we're going to figure out if it's negative or positive after we do the calculation. We get 13 meters per second. Now, because we did get a positive value, this means that this is traveling east now. So 13 meters per second east. Wow, so the helicopter was traveling that direction, then it probably changes direction at some point. All right, that's good. I'm going to skip 4 for now. If I see for time, I'll come back to it because I want to do the other 2 questions. They're a little bit more interesting. Okay, for question number 5, we have a boat increases its speed from 5 meters per second to 7.5 meters per second over a distance of 50 meters. What is the boat's acceleration? Here we don't know anything about directions, but part of the fun in physics is drawing a nice picture. So let's draw a picture. Let's draw our boat. And now we can start to put some of the numbers into letters with directions, but we don't have directions, so we're just going to put numbers. So a boat increases its speed from 5 meters per second. And because they don't give us a direction, this is where you have to assume directions. So you're going to assume that the boat moves to the right. You could have been correct by assuming moving to the left, but usually, most of the time, you better to assume it moves to the right. So let's put east. So again, they didn't give us to us, but we can assume it. And the final velocity is 7.5 meters per second east. So it speeds up, so the vector should be longer. And this whole change of speed was done in a distance, in other words, a displacement of 50 meters. What they're asking us is, what was the acceleration during this change of velocity? Now, because the velocity vector is getting bigger, or in other words, you're speeding up, we are going to be correct if our acceleration is positive, which is to the right. So let's go see which equation is going to be helpful here. In this case, we don't have anything with time, so that's not good. The third one, we have the velocities, we have the distance, we don't have acceleration. So in this case, we're going to be looking at equation 3, which is time independent. That's why I draw a little clock to remind myself that this equation doesn't depend on time. Now let's put in the values. Final velocity is 7.5 square minus 5 square equals to 2a. Leave it as a vector since you don't know for now. Delta d, positive to the right, so put a 50. And to isolate for the acceleration, you're going to divide both sides by 2 times 50. Which is actually just 100, right? So 7.5 square minus 5 square divided by 100 is our acceleration vector. So depending whether we get a positive value or a negative value, that will give us the direction. But if we are correct, we should get a positive value. So let's check. Wow, this is a very slow moving boat. 0.3125 meters per second square, and we got a positive value. So what does that mean? That it's east, which is makes sense because that's what we expected, right? If it was speeding up, so that's correct. Okay, so now we have question 6. Oh, this is nice. This is another spacecraft question, so that's good. I like this one, space. Within 4 seconds of liftoff, a spacecraft that is uniformly accelerating straight upward from rest reaches an altitude of 4.5 times 10 to the power 2 meters up. That was a lot to take in. But at least we know that it moves up. So let's just start to draw our picture. So we know it's moving up and it's uniformly accelerating. Okay, we know it's uniformly accelerating. And it reaches an altitude of 4.5. So we know that that displacement, which is reaching an altitude moving up, is upwards. Delta D, 4.50 times 10 to the power 2 meters up. And this whole altitude was achieved in a time interval of 4 seconds. Now, what is the initial velocity? Do they give it to us? Let's read one more time. Within 4 seconds of liftoff, so that's the time, a spacecraft that is uniformly accelerating, so the accelerating we don't know, but we suspect is moving up because it's moving upwards, right? The acceleration should be going up. So it's uniformly accelerating straight upward from rest. So that's the key part that we had to look at. If it's from rest, this tells you that the initial velocity is actually 0 meters per second. Because you're starting from rest. The final velocity, you don't know, so that's a big question mark. So you don't know the acceleration and you don't have the final velocity. And this question here, the first part is asking us to actually find the acceleration. Let's go look at our equations. We're looking for acceleration and we don't have the final velocity. Oh, the first one is the main one always, right? So we have the altitude, which is the displacement. We know it starts from rest. We don't have acceleration, but we have the time. So we can rearrange equation 1 for acceleration to solve for this. So we're going to use equation 1. And we're going to have to use a convention. In this case, we're going to assume that it is moving up. We're going to take it as a positive value. So north is positive. Okay, so this means our displacement is positive. So we leave it alone. Let's put delta D. Our initial velocity is 0, so this whole term goes to 0. Our acceleration is unknown. So let's leave it as a vector for now. We do know it should be up, but if you're not too sure, just leave it as a vector. And the delta t squared, we have the value, so it's delta t. We'll put in the numbers later, right? For now, what we want to do is rearrange this equation to isolate for the acceleration. So what we do, we're going to divide both sides by a half delta t. So this means that delta D over a half delta T equals to the acceleration. Putting in our values, (4.5 times 10 to the 2 meters, 1 over 2, 4 seconds. Oh, so it's a positive value. So that makes sense. That's good. So we get acceleration is 225 meters per second square. Wow, that's fast. Well, I shouldn't say fast, right? That's a high rate, which makes sense because they're using rocket propulsion, right? So they're using rockets. Makes sense. And because it is a positive value, make sure that you write north. And for the second part in this question, part B, it was asking us, what is the velocity once it reaches this altitude? So the final velocity. Now we have pretty much all the values, so we just have to go look at the formulas and see which one we can use. Now the first one, not so good, because it has nothing to do with final velocity. Right away we check the second one. We're looking for final velocity. We have initial velocity, we have acceleration, and we have the change in time. So see, when you put them in this order, I never ever had to go beyond the third equation. The only thing that we need to be careful with is our convention of up is positive, down is negative. So let's put in the values carefully. Our final velocity equals to, well, our initial velocity started from rest, so that's 0. And our acceleration was north, so we can take that as positive. And putting in the values that we calculated, 225 meters per second square, and the time interval was 4 seconds. So let's calculate this. Uh, 900 meters per second. Wow, that's really fast. And we got a positive value, which makes sense because it was moving upwards, and positive is north, so we can write our vector with the north direction. Now, I am going to skip number 4. I'm a bit tired. I need a break. For number 4, if you need some help, just send me a message and then I can help you out with that one. But, okay, we'll just do it fast. I'll do this one really quickly, okay? Two go-karts, A and B, race each other around a 1 kilometer track. Go-kart A travels at a constant speed. Go-kart B accelerates uniformly from rest at a rate of 0.33 meters per second square. Which go-kart wins the race and by how much time? Actually, this is pretty hard. It's a lot of steps involved. So go-karts is just those little cars that you can rent. You go to the racetrack. So let's have our two cars. A and B. Now, in order to win this race, they need to race each other around a 1 kilometer track. So our distance is going to be 1 kilometer. Now the first one is traveling at a constant speed. Of 20 meters per second. So that's really easy because now we can see how long it takes to cover this distance. But the tricky part is our distance, we should change it into meters. So that's going to be 1,000 meters. So let's see how long it takes for A to travel. So this, we're going to use the formula, speed equals to distance over the time, because it's not accelerating, so we can use this formula. So V equals to delta D over delta T. Isolating for the change in time, So now let's put in the numbers. So 1,000 divided by 20, that's 50. So it's 50 seconds. That's really fast. You should be careful. That's kind of dangerous, no? So that's how long it takes for A. So that's what I was trying to do with pink. Now for B, go-kart B accelerates uniformly from rest at a rate of 0.33 meters per second square. So this one, uniform acceleration. Now, this question is wrong because you can't use this acceleration value in circular motion. So I think there's actually a problem with the question. This question can only work if it was moving in a straight line. But when you move around a circle, you can't be saying this acceleration is 0.33 the whole time. That's nuts. You can't use our equations because our equations only work for one dimension. So it's actually not possible to do the question 4. So Nelson textbook, you've made a mistake. This one cannot do. So if your teacher gives you this question, tell him you can't do this question unless you learn circular motion. So for our purposes, can't. The only way you can do this if we assume that it's a straight line path. Then we can do this question. So if we assume this question to be a straight line path and it's uniformly accelerating, so we can calculate from our formula delta D equals to V initial delta T plus a half A delta T squared. Our displacement is 1,000 meters, and we're going to assume to the right is positive. If they start from rest, so initial velocity is 0, and the acceleration is 0.333, and delta T is what we're trying to find. So we're going to divide it by the coefficient. So if we do this, our change in time will just be 1,000 meters divided by 1 over 2 times 0.333. So let's put this into the calculator. Yeah, see, this doesn't make sense. Because I'm getting the time to be 6,000 seconds. This doesn't make sense. So this question, unless they made a mistake, maybe you can comment on the video, but it doesn't make sense. Yeah. Okay, I'm going to leave it as this, and then leave a comment if you figure this out, but I can't. This question is bad. All right, I'll see you in the next one. Bye-bye.